So let's start our introductory part of electrostatics, and we'll eventually be talking about Coulomb's law, but I want to kind of list the topics that we're going to start with. Coulomb's law, the electric field, divergence and curl of electrostatic fields, Gauss's law, electric potential, work and energy in electrostatics, and multipole expansion of the potential. First of all, let's talk about charge. All matter is composed of what I call really small, compact particles, the electron. It has no spatial structure seen so far, and it's your basic point charge, or point object. The proton has substructure, but it's extremely small scale. Remember, the charge of the electron is called E, and that's a negative number. And so if we get the charge on the proton, we put a minus sign, which gives us a positive charge. They have equal and opposite charges. To within an accuracy of 1 part in 10 to the 20th, the magnitude of those two charges are equal. The electron has negative charge, and its magnitude is given by this quantity here. We usually go with about minus 1.6 times 10 to the 19th. And the units of charge is coulombs, and you may remember from beginning physics that 1 coulomb is huge. The sign we use, so the fact that this is a minus sign, we blame Ben Franklin for that. He could have used positive, but he didn't, so we end up with E being minus. So there's 4 important facts. All of these are determined experimentally. First one is that charge is a scalar, does not depend on direction. There's conservation of charge. The algebraic sum of charges, the net charge of an isolated system, never changes. As far as we know, that's true of the whole universe. Total charge in the universe is conserved. Quantization, charge comes in units of E, both on the proton and the electron, this E. And so all charged bodies have charges that are integer multiples of this quantum of charge. This is what you learned in early science classes, that like charges repel, unlike charges attract. People make a big deal about this, and it is important, but realize this is just an experimental observation. Coulomb's law is the force law between two charges, and so if we have two charges, Q1 and Q2, we would write that the force between the charges is K times the product of the two charges times some magnitude of a vector here, which we'll talk about, and the unit vector. This is pretty vague. The unit vector is defined as the appropriate unit vector, and this constant K does have a fixed value, and that's 1 over 4 pi epsilon naught in the MKS system. And if you look at what epsilon naught is, it's this quantity here. K, if you take 1 over 4 pi epsilon naught, with this being epsilon naught, you get K approximately equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. And because this is easier to remember, and because we just want to put a constant in front of this equation, we normally just write this, but sometimes we put in epsilon 0. Starting with what I just gave you, this definition, what does this actually mean? The warning that I'm giving you is that this is a very fuzzy definition of the Coulomb's law, and we're going to refine that quite a bit. The first thing is, if we look carefully at this statement, we've got this Q1, Q2, and we've got this R1, R2, and so we first realize that those give us the locations of Q1, these vectors, and R2 gives the location of Q2. So to write that in a way that is clear, we just make Q1 be located at R1, so it's a function of that vector, only in the sense that it points or is located at this location. And the same goes for Q2, where we have R2 in this position. Well, that means there's an origin somewhere. If you're going to define these vectors, we need a diagram, and so that's simple. We have some origin, and we have the two charges located at these 2 points. And the vectors R1 and R2 just simply connect the origin to those points. If we look at the denominator, this magnitude of R1 minus R2 squared, that's not much help in terms of understanding what this difference vector might be. First of all, realize that we can just switch the order, and because this is the magnitude, we get the same answer, and then when we square it, we get the same answer. For clarity, as I'll show later, we're going to stick with this order of R1, R2. Going back to our fuzzy, or what I call a stinker, of a definition of Coulomb's law, let's start with asking what charge is actually experiencing this force up here. This is a very ambiguous statement, so we've got to clarify some things. And the first thing is we have to do a better job of defining funny r. And funny r, of course, is related to the unit vector, which is the vector r divided by the magnitude of that vector. This funny r is equal to r1 minus r2. So now we're getting a little more clear about what this difference in the two positions are. If we call those the positions of those two charges, which way does this vector point? So we have r1, r2, and we want to know what direction that points. Draw the picture, look at our definitions, look at the two vectors, and say what direction is r1 minus r2. Well, there's lots of ways of graphically finding that direction, but the simplest way is just to take r2, flip it, and put it at the endpoint of r1, so you're adding r1 minus r2. And so if I just draw a parallel here, it's not going to be pretty. But here is minus r2. So now if we connect O to this vector here, we get r1 plus a minus r2. So our funny r is this vector here. Well, we want to draw it from q2 to q1, so we just take this vector and put it up here. Here is our vector, and the unit vector, of course, would be parallel to that and have just unit length. If we take the case where we think these are the same sign, then we know that there's repulsion. If r and r hat are defined as we've shown here, then what force are we talking about? Which charge are we looking at the force? So this should be a vector. Well, what it is, it must be the force on q1 due to q2. Why is that? Okay, if they're repelling, then of course this charge here would be pushed in that direction. That's the force on q1 due to this charge here. If you tried to reverse it and say, what is the force due to this charge on this one? Repulsion would say that it should be this way. But our equation says that we should be in the same direction as r hat. So therefore, we must be talking about the force on q1 due to q2. If we want to be unambiguous, we have to say what charge the force is acting on and what is it due to. So for 2-point charges, the force on q1 due to q2 is equal to, alright, here we go, our k, our two q's that are located at r1 and r2, divided by the distance between them, squared, or the magnitude of this difference vector, squared, times the unit vector that points from q2 to q1. That's how we reasoned this to be. Well, just remember what I just said, that this quantity here that shows up in the denominator is a magnitude, and it equals the distance between the charges. So if you wanted to, you could say that the denominator is just this distance squared. So that gives us quantity in this position here. That distance is the magnitude of the vector r. And so we can write the force on q1 due to q2 as being k q1 q2 divided by the length of funny r squared times the unit vector funny r hat. So this quantity here, the vector r, just to beat it to death, is r1 minus r2. This definition is clear. It tells you what charge we're pushing due to the presence of another charge. It gives you the direction. It gives you the magnitude. With all of that information, we have a complete picture of Coulomb's law. If we take a look at the picture that we've drawn, that's this over here where we've used the 2 and the 1 to designate these two charges. I just want to transform that to another picture that is most often used in textbooks. And that is, you change the charge that is generating an electric field to a prime, and you call that the source charge. That source charge simply means that it is going to influence any charge that you put in the vicinity, in the neighborhood. That's at r prime, and that's what you call the source point. Now you have a probe charge, which we'll call Q. And this is at the position R, whereas the source charge is at the source point R prime. Well, just as we did before, we defined this funny R vector that goes from the source point to the field point, and that's this quantity here. So just translating what we had before in terms of 1s and 2s, then the force on Q, the test charge, due to Q prime, the source charge, will just be equal to KQ of R, which is where Q is, Q prime of R prime, which is where Q prime is, and then we put in the vector R magnitude squared times the unit vector R hat. And just as we did before, we define this funny R as being the vector R minus R prime, and that means it points from R prime to the point R. So in words, the force exerted on a test charge Q in the neighborhood of a point source charge Q prime is proportional to the product of the two charges, so that's this quantity here. It's proportional to the inverse of the square of the distance between the two charges. And we know how to get that. We have the vector that goes between R prime and R, that's our funny R. We take the magnitude of that squared, which is equal to the square of this vector here, because that is equal to the R vector. This is a positive scalar at all times, and the unit vector R hat, points along the line between Q prime and Q. So this is a repeat of the Coulomb's law, and it's clear that we know where the force is acting. It's acting on Q. We know the source, which is Q prime. So this language is important when we start talking about electric fields. So some very simple corollaries are that if these charges are of the same sign, then the force on Q due to Q prime is along that unit vector direction, and that's consistent with a repulsive force. If they differ in sign, so let's say the sign of Q prime is minus the sign of Q, then the force on Q due to Q prime is in the minus R hat direction. Both results are automatically taken care of by this product because it will change from plus to minus depending on these conditions above. We want to realize then that changing the sign changes the direction of the force, and that's all taken care of by this product. Well, there's another property of charge, and that is superposition. So we'll just change some notation, keep things interesting. Consider the forces on a charge capital Q from several Q's. And so the question is, how will this be found? And the answer, again experimentally, is determined to be superposition. Superposition simply means we add up the individual forces. So the total force then is the superposition or sum over the Q's from Q1 to Qj or Qn acting on a charge plus Q. And so this will be determined from experiment and gives us a principle which is very important in electrostatics. So here's how it looks. Here's our old picture here. We just had two charges, and we knew how to get the force on this charge due to this one. Okay, now our Q primes are going to be these Q sub i's. So they are the source charges which are acting on this charge over here. So we'll just take the coordinate system to give us the position of all of those charges out here. We'll call R sub Q the position of the Q charge. And just for illustration, suppose we add up all those charges and we get this electrostatic or total charge pointing in this direction here, just for illustration. So what are these R sub i's? Well, they're just simply R sub Q minus R sub I. So this would be like over here we have R minus R prime. R sub Q is the field point, and this is the source point. But there's a whole bunch of these. So when we calculate the total force, say for n of these things, all we do is sum over the Q sub i's. And so that's shown right here. So we can bring the constant K outside. We sum all of those single forces into this sum from 1 to capital N. So here's our single Q, so that doesn't change. That's always there. You could bring it outside if you wish, by the way. And then you have all of the Q sub i's divided by the R sub I, funny R sub I squared, times the funny r hat. So realize that both of these are changing as you index I. This is changing because the position of Q changes and the magnitude is likely to change too. And so you add up all those forces and the total will be F on Q due to all of the Q sub I. Let's take an example. Let's consider a set of n charges. All these charges are the same, and so these are all Q. They're situated on a circle, equally spaced, distributed on this circle around a single charge, capital Q. The question is, what is the net force on that charge at the center? We'll eventually be testing this for n equals 3. So let's say that x sub k, y sub k, those are the coordinates of the qk. For example, if we call this 0, k equals 0, then that will be the q that's on the y-axis. We rotate these charges until we have a charge right on the y-axis. If we count the charges that remain, so here's 1, let's say we go up to 3, this would be 1, 2, 3. So the maximum in terms of the number of charges beyond this one here, this would be 1 and this would be 2. If we call this k, k equals 0, k equals 1, k equals 2, then k max is equal to 3 minus 1, or n minus 1. So this is k max for the distribution of charge that we have. Let me repeat. If we have n total charges, then k max is equal to n minus 1, and that corresponds to the last charge going around the circle clockwise. Well, we need the vector that points from k sub q to the charge in the center. I'm going to propose what that is. It's going to be these cosine-sine components that will have k and n inside. And once we pick an n, then k is going to index through the values which will give us all of the rest of the charge. Now this minus sign here is because if you look at the vector which goes from the origin to a particular charge, so let's say this vector here, the force is going to be in the opposite direction. So if these are two positive charges, then the vector which will give us the force on Q due to this charge here will actually be minus r sub k. I'm being a little sloppy here. The coordinates of this position are x2, y2. That's the vector that goes from here to here. But if these are the same sign, the force is in this direction. So if I want the direction of the force, I have to put a minus sign. And that's the origin of this minus sign here. So we'll take that vector to give us the direction of the force acting on capital Q. Okay, so that points from the k sub q to Q, and that's very similar to what we were doing when we defined Coulomb's law. This is the source charge, this is the field charge, so that's why we put it in this direction. Given this r sub k, the vector from the source point to the field point, let's take a look at these forces. We want the force on Q due to the kth charge, and so we'll call it this quantity here. We know that that's going to be the usual factors here, and I'm using capital K to distinguish from this little k, so this is the k in Coulomb's law. The way we've directed our r hat, or r sub k, this will give us the direction of the force on Q due to little q. These will be given by the same quantity, and then we write our r hat in terms of the r vector, which is right here, divided by the magnitude of r sub k. We have to realize that the magnitude of r sub k, they're all the same, is equal to capital R, the radius of the circle. That means that this factor here cancels this one, and so we're left then with the expression here. And so notice that it's a sine and cosine with k being indexed as we index k. So what is the total force? Well, it's going to be the sum over k, but we have to be a little careful about that. So here's our force on Q due to all of the point charges, and we sum from 0 to n minus 1. 0 gives us the charge along the y-axis because we called that the 0 position, and remember there's the maximum k is n minus 1. If we have n equal 3, that's 0, that's 1, that's 2, and that's the maximum position for k. Okay, so let's take n equal 3, so we'll look at the simple case that we've drawn here. And we have the prefactor, and we index through little k. So k equals 0, so that's this vector right here. K equals 1, that's this vector right here. And here's k equals 2, that's this vector right here. And we're summing over them because that's what this summation tells you to do. So you're getting the total force by adding up all the applied forces. So let's do that. Let's evaluate these vectors, or these components. Sine of 0 is 0. Cosine of 0 is 1. And then we take these, we have to basically do them, and that's square root of 3 over 2, and then minus a half, and so on. So we get this right here. Well, let's bring the minus sign inside because I want to show you what this looks like. So I've just put the minus sign inside, so I've multiplied all of the factors by minus 1 to give us a set of vectors. And look at this one right here. This is the force on Q due to this charge, because that's our 0 position. Well, notice what it is. It has no x component, which is what you would expect, and it has a minus 1 component, which is down. So that gives you the right direction for the force due to this charge acting on this charge. Well, just to qualitatively look at this vector here, and we're talking now about the force due to this charge acting on this. And you'll notice that it has a negative x component, so it's pushing this charge this way in the x direction, and it has a positive force in the y direction. So as a result, this charge would be pushed in that direction. Now I've shown it exactly along here, but you get the point. Now do the same thing for over here. It's going to push it into this quadrant right here. Well, look what we have. We have plus, plus. Add them all up, and you get 0. So the net force on Q due to these three charges is a 0 force. Well, let's take a look at what Mathematica might tell us about these forces. So here we have then our diagram for n equal 3, and we'd like to look at these forces. And so what I have here is a cell that gives us the force vector for any n as a function of k. So this is the kth force for a given n. This will be in the direction of the force on Q due to the k charge. I'm going to make a table of these forces so that you can see what they look like. And we're not going to take too many because the table gets pretty big. So we're going to go from n equal 2 to 8. Realize that n equal 2 corresponds to a charge here and here. So there's only two charges. So let's evaluate that. And here's all the vectors. And the first one is for n equal 2. And so there's two forces. And the first one is the force due to this charge acting on this charge, and you'll notice that it's 0 in the x direction and in the minus 1 direction, so it's pushing the charge down. This vector here corresponds to the force. If we put a charge here, it'll push up, and so that's this one right here. Well, hint, hint, look at the sum of these two. We're going to get 0. Here's the one we just did. This is 3 charges. Here's 4 charges, and so on. So we'll see how these add up. So here's his 8. This is the 8 set of charges, and let's see, 1, 2, 3, 4, 5, 6, 7, 8 components for the different forces due to those 8 charges. Okay, so now let's look at the total force, and we're going to plot the positions of the charges and the corresponding total force for those positions. I don't have time to go through the code, but we're going to use the function manipulate, and what that does is allows us to change the value of n, and I'll show you what those are. Forget this null here. So here's n equal 2, here's the geometry that we just showed, here's the one on top, here's the one on the bottom. We get 0 force, which is what we would expect from the vectors that we got above. Okay, here's n equal 3, the one we did already, 0 force. 4, 5, 6, 7, 8, 9, 10, and so on. If we just slide this, we keep adding charges, and we keep getting zeros. And so I took this to 199. You still get 0. Regardless of the number of charges in that ring, as long as we distribute them in even spacings, we get 0 for the force. Now I just want to point out something. Let's go to 8. Any even number, we always have opposing positions. So those two charges will always give 0 for the contribution from those two charges. Keep going. These two give 0, these two give 0, these two give 0, and so you end up with 0. So even charges are simple. You always have symmetry such that you get 0 force. Okay, now what about if we remove the top charge? Let's remove that charge right there. The way to do that is just simply remove k equals 0 component, which is what this top charge corresponds to. We remove that charge by just summing from 1 to the same value. Okay, so I'll run this. Here's our result. What's missing right here is the charge up here. You can't see that. And what we get is a force that is in the upward direction, and we'll see how that happens. So now we're going to increase n. So start 2, 3. Okay, now what's missing is this charge up here. Notice which direction the force is. It's up, up, up. Okay, see what's missing? See? It's this charge right here. So why is it up? Because this one isn't there to push down. And so what's missing is the force due to this charge pushing the charge down. We subtract it and we get this force remaining. And so we can just keep going. We can go all up to 199, go back and forth, back and forth. We always have this 1 sitting here and a 0 here. The 0 is because it's on the symmetry axis, the y-axis, so there's no x component to that force. And we always have plus 1 because we're missing that point there. If we go to the equation as it is, for the nth number of charges, here's the force due to the kth charge, and this is the total that sums those all up. I want to show you what happens on Mathematica. N is totally unspecified. We have not told Mathematica what n is. Look what you get. This is just the nth force. You get 0. So let me just repeat. I'll suppress this. This is the total force acting on that charge, no matter what n is. N could be zillions, and you'd still get 0. Mathematica is smarter than we have been. First, I've already shown you that if n is even, there's no question. Symmetry will give you total cancellation. But what about n equals odd? Well, one can use what's called rotational symmetry. One has to be very careful to generate this cancellation argument. And I'll try to give you quickly what that looks like. So let's go back here. So we see the single points. And so if I were like this, n equal 23 say, and I wanted to argue even with odd numbers, we should get 0. The argument is this: suppose that I have these charges distributed as they are, and I have a net force. It isn't 0. So because the positions of these things, and we know odd numbers might give us a value of the force, we assume that it exists. Now, this ring of charge has rotational symmetry. It does not have inversion symmetry, which means that if you put a mirror up, you get the same thing. It has rotational symmetry, which means that if you rotate this in a frame of reference where you rotate with it, you can't tell the charge has changed. And that's what we call rotational symmetry. So if there was no change, then if you have this non-zero force, it should change direction as you rotate, which means that you've destroyed the rotational symmetry. So that argument says that you can't have a force if you have rotational symmetry, which we do. So that means that even for odd n, you won't have a force. We have shown it by brute force by doing these summations and finding the vectors that define the directions of the forces. So brute force, we get 0, 0, no matter what n is. And if you say, well, wait a minute, let's make n bigger. Okay, let's make it 2,000. And now we're 2. Look at this, look at this, look at this, look at this. We go all the way to 2,000. We still get 0. The brute force method, for any n that you're willing to wait and calculate, will give you this 0, 0, which means there's no force. The symmetry arguments for both even and odd tell you that you should get 0 force also. And the only reason that it works is because you have symmetry, because you have the spacings all the same. So that's why you have rotational symmetry. But next time we'll pick up on the electric field.